Well, good afternoon, everyone. Welcome to the Center for Fine Print Research and our lunchtime seminars. Very pleased and excited to welcome Ming from the center, who's working with the Graphene Lab with Dr. Nazmul Karim and the team. And Ming is working on development of graphene-based auxetic composite materials, and you'll hear more about his research and his work in a moment. Just wanted to welcome everyone. Thank you for joining us today. Just a little bit of housekeeping there. The session will be recorded. So in this, and like all this lunchtime seminars, they will be available on our website, from our website, cfpr.ue.ac.uk, for anyone who wants to listen to it again or wants to forward it to someone. Please ask questions as Ming is presenting in the chat function or the Q&A function. Dr. Nazmul Karim will be leading the Q&A session after Ming's talk. So I would like to introduce Ming and invite him to join us on the stage. And then Dr. Nazmul Karim is going to join us at the end of the session, and we'll ask some questions and we'll lead the Q&A as well. So welcome, Ming. And Ming is returning to Hong Kong in August. So thank you again for all your input that you've had in the center, and over to you for your presentation.
Thank you. So today I'm going to talk a little bit about my PhD research, which is about developing the three-dimensional composite with nearly isotropic negative Poisson's ratio by random inclusions. Let me start with give you some background information. The Poisson's ratio measures the Poisson effect of the materials. It is the negative of the ratio of lateral strain to longitudinal strain of a material under stretch or compression. It can be calculated from this equation. So in nature, most of the materials, not just in nature, just in almost all the conventional materials, they are conventional materials because they have positive Poisson's ratio, which means when you stretch it, as you can see in this figure, when you stretch it, it contracts in this. When you stretch in the lateral direction, it will contract in the vertical direction. But when you compress it, it expands. So these materials, they are conventional and they have positive Poisson's ratio. But for auxetic materials, they have negative Poisson's ratio. They will show an opposite deformation behavior compared with conventional materials. If you can see here in this figure, for auxetic material, when you stretch it, it expands, but when you compress it, it becomes smaller. So some natural materials have been found to exhibit negative Poisson's ratio, and one typical example is a cat skin. So some doctors, they measured the Poisson ratio of cat skin and cow cat skin, I think in 1930s. So they found it's actually auxetic. So, but this type of material have not been manually made until 1987, which Professor Lakes, they made one kind of auxetic foams, which shows negative Poisson's ratio. After that, this material becomes more and more popular. So many researchers are doing research about making man-made auxetic materials. And up to date, we have successfully manufactured auxetic foams, textiles, composites, and even some metals and some plastic structures. So by having this unusual deformation behavior, the auxetic materials are able to have some very special properties and some enhanced performance. The first one, the most important one, is the enhanced energy absorption and better indentation resistance. As you can see in this figure, when you giving a force to the material, for a conventional material, when you press it, it's actually because it expands in other directions, so it becomes density of the material becomes smaller. But for auxetic material, when you give a force to it, it becomes actually denser because of the densification of the materials. Another thing, like auxetic material has synclastic curvature and shape fading. This is very useful for making auxetic textiles. For conventional textile fabrics, when you bend it or curve it, it normally has this kind of saddle shape curvature. But for auxetic material, they have synclastic curvature, so which gives the material, the fabric, very good shape fading when you make something like bras. Another example is the pore opening effect of the auxetic fabric. So when they make the fabric with this kind of reentrant hexagonal structure as shown in this left corner figure, when you stretch it, it expands in the center to open the pore. This can be used in some medical applications. But in my PhD research, I focus on making auxetic composite, and among many types of man-made auxetic materials, auxetic composites have shown great interest to researchers because the composite materials can combine different materials in pre-designed geometry and be tailor-made to meet specific requirements. So in all these, there are many types of auxetic composites, but my group is focusing on making auxetic textile and structure reinforced composite. This kind of composite is made by using textile reinforcement and some polymer matrix. The auxetic effect is realized by using auxetic structures. The deformation of these auxetic structures will create the overall auxetic effect of the whole composite. And up-to-date different types of auxetic composite reinforced by auxetic textiles or structures have been developed. There are auxetic fiber reinforced composite, auxetic fabric reinforced composite, and three-dimensional auxetic textile reinforced composite, and three-dimensional auxetic composite with inclusions. So my work, my PhD research is focusing on this type, three-dimensional auxetic composite with inclusions. This type of composite has been theoretically studied for a long time. Many literatures and research have discussed this kind of composite in a numerically way or financial element analysis. So, and this figure, if you can see from this figure, these figures are from one of our previous work. We build this mode of this reentrant triangle and the reentrant hexagonal in a 2D plane of some kind of materials, just giving a plastic. So when we compress it, it can deform and contract in the lateral direction, which shows auxetic effect of this overall structure. So inclusions with various auxetic structures, not just this reentrant triangle and reentrant hexagonal and others, rotating squares, ellipses, etc., have been theoretically studied. And all these literatures, they proved that by adding this kind of structure inside the material can help reduce the Poisson's ratio and even realize a negative Poisson's ratio. So further to our previous simulation, we did another simulation in terms of regarding to the two-dimensional structure. So here, if you can see here in this figure, we put many of these reentrant triangle structures inside this plane. This is a two-dimensional figure, and we put them in a random way. So the distribution and orientation of the triangles, they just be randomly put in there. And when we give them a force, this loading direction from the top to the bottom, we can clearly see the contraction in the lateral direction. So from this simulation, we found that the number of inclusions and the contrast in stiffness of constituent inclusions and the matrix need to be sufficiently high to realize the auxetic effect of the composite. Although this type of auxetic composite has been theoretically studied for a long time, and many works have proposed many structures to make this kind of composite, but they are only being theoretically studied. So my PhD work focuses on like trying to make one real composite with this structure. So in the first step, I did a simulation of this kind of three-dimensional composite. So I made the inclusion with reentrant triangle cross section. So I made this, if you want to see from the left figure, I made this mode first. So made this inclusion prism. This inclusion with this prism having reentrant triangle cross section and with a length of around like 6 millimeter. Then we add around 400, 500, 600, and 700 and 800 inclusions inside this matrix. And then we import this mode to the finite element analysis software, Abacus, to mesh it to create this FE simulation. And then we add a force to compress it. If you can see from the right-hand figure, the gap between the red line and the blue rectangle, there is a very small gap, if you can see it. This shows the lateral contraction of these overall structures, so which proves that this type of composite can have auxetic effect. So after that, I started to actually make this type of composite. But before making this, there is one important thing is like what kind of material I can use to make this composite. As I mentioned before, there is one critical thing of achieving this auxetic behavior is the stiffness difference between the inclusion and the matrix. To meet these basic requirements, I used one layer carbon fiber epoxy composite as a material for making inclusions, and the silicon rubber as a matrix of the overall composite. The combination of the carbon fiber epoxy composite and the silicon rubber can create a relatively large stiffness difference. And in the same time, the one layer carbon fiber composite is still having a little bit like flexibility. You can compress, it can deform like slightly to create this deformation of this overall composite. So this is the manufacturing process of the composite. So in the first step, we make this composite prism with the carbon fiber prepreg. And then we cut this long prism to become a short prism. And then we seal the two ends of each of these reentrant triangle prism. And the sealing is quite necessary because if we don't seal the two ends of this reentrant prism and we leave it open, when we add into the silicon gel, the silicon gel will get into the inclusion, get into the prism, which makes the composite just become one silicon composite with some carbon fiber plate. It will not create this reentrant triangle structure inside the matrix to create the auxetic effect. So after we seal it, we put into the mold with the silicon gel, then just leave it for cure to get this composite. But as you may know, the carbon fiber is having a very high modulus, which makes it quite difficult to bend to fit this mode, this reentrant triangle mode directly. So another problem is like even when we force it to fit this mode, but like it's quite difficult to demold it after the curing. So in our process, like we use a 3-stage method, which is quite silly, but which is quite silly, stupid, but like it's useful. It's working for making this kind of composite. So we in the first step, we use a mold with this wave surface. If you can see from these two figures, the right-hand one is a cross-section of the mold. It has this wave shape. So we put these prepregs onto this mold to make some plates, carbon fiber plates with this V-shape curvature as a structure. Then we cut these plates along this wave direction to get many V-shaped strips. Then we stick every 3 strips on a 3-dimensional mold to get one reentry triangle prism. After that, we cut many of these long prisms to get one small inclusions, as shown in this left-hand figure. And we actually manufactured many composites with different inclusion numbers, different prism lengths, and different materials. But here I just show one example of our work. So after we get this composite, we did a compression test for this composite. The compression test followed the standard test method for rubber properties, as the silicon is kind of rubber. Using Instron 5566 universal testing machine, the samples were compressed to 20% of compression strain, and the center of the sample was marked for measuring. And this figure here shows the compression setup. Between this composite and the compression plate, we need to put like sandpaper to prevent the slippage of these silicon materials. So to record this deformation process from compression test and to measure the Poisson's ratio, we put a camera just 50 centimeter in front of the sample to record the lateral and vertical deformation. And after the test, the video recorded were processed to extract each frame of the video, and pictures were selected with 1 second interval. Then we measure the deformation of the composite from these figures to get the height and width variation, and then calculate the Poisson's ratio. Here shows the one result of the one type of the composite we made. From this figure, we can see very clearly, like there are some area the Poisson's ratios are negative, but the majority of these are positive, of course. And we measured the Poisson's ratio in X direction, Y direction, and Z direction to check the isotropic property of the composite. Basically, these 3 lines, they are quite similar, and which shows they have like nearly isotropic property. For this orange line, it shows the Poisson's ratio variation of the pure silicon. We can see it has 2 stages. Like firstly, it increases rapidly with the compression, then it gradually increases after it reaches around like 0.5 of the Poisson's ratio. Then it gradually increases with further compression. But for the composite, the deformation process can be divided into 4 stages. In the first stage, the Poisson's ratio increases a little bit, because during this stage, the inclusion inside the composites, they do not deform, but the silicon, they deforms to expand, but the inclusion, they don't deform like to have an inward deformation to create the lateral contraction of the composite. So the overall composite shows positive Poisson's ratio, but after further compression, the inclusions start to deform to create the lateral contraction of the composite. So the overall composite start to having negative Poisson's ratio gradually. After all the inclusions are fully deformed, the deformation of the whole composite becomes a deformation of the silicon again. So the Poisson's ratio starts to increase and increase as the pure silicon. So it has the third stage and fourth stage deformation. This figure shows the influence of the inclusion numbers on the Poisson's ratio and the optimization process of our experiment. So as you can see, for this composite with like more inclusions inside the matrix, the composite can get better auxetic effect and even smaller positive Poisson's ratio after they become like positive. The reason for this is quite straightforward, because like more inclusions inside the matrix, it provides more space for the lateral contraction or the deformation of the inclusion, and the composite. So it gets more space for the composite to have lateral contraction. But there is one phenomenon shows that samples with 700 and 800 inclusions have higher positive Poisson's ratio than others due to the overcrowding of the inclusions. You can see from the figure, the orange and blue lines, they have lower negative Poisson's ratio at the beginning of this compression, but when it comes to like around like 18% or 19% of the compression strain, they become higher than the previous the composite with less inclusions. If you ask, this figure shows the overcrowding of the inclusions. When compression to this, when the composite is having too many of these inclusions, they start to like push each other, to push the neighboring inclusions, which gives extra expansion of the composite and leading to the higher Poisson's ratio. This figure gives a compression stress of the composite. The pure silicon rubber has the lowest compression performance, and the composite with more inclusions has better compression performance. It can be quite straightforward to see from this figure, but like the problem of this composite is the mechanical properties. They don't like increase a lot, because like even when we put 800 inclusions, it's still like a low volume fractions of the carbon fiber, and it's actually even when we put more inclusions, it actually puts more air inside these composites, so it doesn't help with the mechanical properties. So this is one problem of our composite. So in conclusion, the auxetic effect of the soft silicon composite can be achieved by embedding re-entry equilateral inclusions made from carbon fiber prepreg. The composite samples only exhibit auxetic effect in the initial stage of compression. The Poisson's ratio becomes positive at around 5 to 8% of the compression strain. More inclusions can provide the composite with better auxetic effect during the initial compression stage. The composite samples show better compression performance than pure silicon rubber. And that's all of my presentation. Thank you.
Hello, Dr. Zhang. Thank you for your presentation.
Hello.
Hello. Sorry, my camera is not turned on. So if you can hear me, that will be good.
Yeah, I can hear.
Okay, good. I have a couple of questions here, if you don't mind. First of all, not sure I joined early enough, so I had no information on the dimensions of those inclusions. Did you carry out
The dimension.
Yes.
Yeah, because I deleted some slides for this presentation. I didn't put the dimension information in here. The size of the length of the inclusion is 6 millimeter, and
well, we have to be careful here because they were triangular. So when you say 6 millimeter,
I mean, for the inclusion for the prism, the length is 6 millimeter.
Yes.
But
Okay.
for this triangle ribs, it has 6 ribs. Like it's a reentrant triangle, it has 6 ribs. For each rib, the length is around 4 millimeter.
Okay. Right. I was also wondering about effects of orientations of these inclusions. I don't know if you had any means of controlling the orientations.
No, it's by random. It has
seems to be
random
quite
orientation and
random.
distribution.
Yes. So it was purely randomized.
Yes.
Well, we can't really say how much randomized.
No, we can't say how much is random, but
Yes.
you just put in there randomly.
You just put the stuff in there and hoped for the best.
But for the simulation, the random orientation and the distribution is generalized by the computer. So
yes.
I input this data in the coordinates of this inclusion, and then the computer generates all these coordinates for all inclusions and orientations for all inclusions. Then I get the inclusions, set the coordinates and orientation of each inclusions to get these random.
Yes, of course. The computer will do that, but the manufacturing process, it's a different thing altogether, isn't it?
Yes.
Okay. And I noticed one of the videos where you did a compression test, okay? And I was wondering if there is any image which just managed to capture the test and at the point where you might have achieved a negative Poisson's ratio.
Oh, yes. I have these images, but I didn't put into this slide.
Okay.
Because this image, I would just submit to a paper.
Oh, I see. Well, the thing I'm usually concerned about is the accuracy with which you can measure the Poisson's ratio by determining the epsilon y, epsilon x ratio. So how did you ensure there was a high degree of accuracy?
So, yes, in terms of the calculation accuracy, I don't do the calculation by hand or by my eyes. We developed a program, a software to analyze the image, recorded from extracted
Okay.
from this film and this video. Then this program calculates the length and width deformation
in terms of pixels,
by pixel variation.
Was this in terms of counting number of pixels in a particular orientation or direction?
Yes.
Okay. Right. I think I must give a chance to other people. I don't.
Yeah. Thank you. Thank you for your questions.
Can you hear me?
Yeah.
Yeah, I've just got a question to ask you, Mint. So, I'm just wondering what are the real life application of auxetic textiles?
For auxetic textiles, like, well, like I didn't do auxetic textiles, but I still know something. There is one of these, but it's not quite. It's not used commercially. It's not useful, but for experimental, it's quite useful. Like they in my group, they used to develop one kind of fabric which can grow up with the teat grow up. So, which means like because like for auxetic fabric, when you stretch it, it becomes like expands in another direction, right? So when you make kind of clothes with this auxetic fabric, when your kids grow up, become bigger, the clothes will automatically having a larger size. So you don't need to buy extra clothes for your kids, which is quite interesting, but it's commercially it's not good because you can't sell more clothes. For other applications, like there is one like for auxetic yarn, they are saying they can use it as for the dental. How to say that? There's some kind of dental line used to clean your teeth. When you use auxetic yarn, because when you stretch it, it expands, so it has better cleaning effect. And for medical application, like like I mentioned in that figure, this kind of pore opening effect. There's one of my senior, they did a research about like doing some kind of drug releasing fabrics by this auxetic fabric, because they have better pore opening effects. When the wound swells, it actually stretches the fabric so to open a pore to release medicine to your wound. These kind of applications.
Very interesting application. I think like the floss and especially the clothing. I think it will open up the scope for like making the clothing sustainable, like a circular economy, which is really important at the moment. So yeah, it's really a great area, I think. Yeah. And do you know, like, if you apply graphene onto it, is there any scope to improve the performance of it?
You buy like when I come to CFPR, I talk to Nazma saying like adding graphene to it. It is because currently I'm using a carbon fiber to make the inclusion, which makes the inclusion is kind of anisotropic materials. The property of this inclusion is not isotropic, but if I add graphene into the silicon or other materials or any other materials to make the inclusion from that will form a isotropic material for the inclusions. So it will maybe giving better auxetic performance to the composite, but like I'm not sure.
Yeah, it's nice. Thanks for the nice explanation. Thank you.
Thank you.
I haven't got any more questions. Does anybody else have got any other question to ask?
Question from Arno, which is, what is the objective here? Is it proof of concept or minimize Poisson's?
Yes, it's proof of concept, because not just proof. Like this composite is only, like I said before, it's only be theoretically studied. It's not actually made of this kind of composite. So like we are trying to prove of this concept. You can't just like do simulation work. So we actually made this composite.
Okay. Also, Arno was asking, wouldn't the NPR be improved with a much less stiff material for the inclusion? In fact, as compliant as possible.
No, this is like, but there is a limit of these modulars. But if one of the most important thing to achieve the negative Poisson ratio is we need to create the large gap between the modulars of the inclusion and the matrix. If the gap is too small, it can't have the auxetic effect. This has been like proven by many literatures, and also in my in my simulation, it's a same result. If they include the modulus of the inclusion is too small, you can't.
Okay, well, thank you. Right, are there any other questions for Ming, or even for Nazmul, or for Shayla? John?
Yes, I was
please.
just going to ask Dr. Zhang again whether the narrow window of auxeticity, which you showed in your graphs, yes?
Yes.
Poses a limitation, it's a severe limitation because you really don't have much room to play with using this material or this particular method, at least of manufacture.
Sorry, I didn't hear clear.
I'm sorry, I said when you showed your graphs of auxeticity, yes, negative Poisson's ratio.
Yeah.
Yes, you had a very narrow window.
Mm-hmm.
Yep.
Yeah.
Where this material was auxetic.
Yeah.
Isn't it?
Yes. So I don't understand what's your question.
My question is that since that window is very narrow,
mm-hmm.
this material cannot be used extensively to show it is going to be continuously auxetic over a wide range of stress applications, for instance.
Yeah, for this composite, yeah.
Yep.
Yeah. For this composite, it only has a very narrow window for having negative Poisson's ratio.
Yes. Is that not a severe limitation on its usefulness?
This limitation, because the key, the intrinsic reason of having auxetic performance of this composite is the auxetic performance of this composite coming from the deformation of the inclusion inside the composite. So if you get more space, more inclusions inside the composite, then you can have wider window for auxetic effect. But the limitation is right now, based on our lab's equipment and technique, we only can manufacture the inclusion with that size and that shape. So it only can provide the composite with the negative Poisson's ratio with that small window. But technically, from the simulation, if we get like the inclusion smaller and we put as much as possible, like for our sample, the size for the whole composite is 10 centimeter by 10 centimeter by 5 centimeter. If we put for each centimeter, if we put 2, which means because we have simulation, we put around 2,000 inclusions inside the composite, the auxetic effect will be much wider and better. Yes. But for practical, we can't make that.
Is it not possible to envisage the possibility of using 3D printing to put in these inclusions?
The problem of 3D printing is that the 3D printing, when you do 3D printing, you get some kind of you can't do this void space inside the inclusion. You understand what I'm saying? Because when you do 3D printing is not good for making structure with this void inside the inclusion, which is important.
Thank you, Ming. Thanks. Sorry, I had to go. I'm not sure if all the questions have been covered. So there's one question: is what material model you apply for the triangular composite in Abacus?
Sorry?
So I'm not sure if you can see that question Q and A. Yeah. So what material
model for the triangular composite? Actually, the simulation is not just directly not like we actually simulate the exact our experiment. I make this inclusion by splitting into 3 plates. So in the SolidWorks I create this with 3. Firstly, I draw this triangle, then I get this inclusion, then input into, but then I split it to become like 3 V-shaped plates. Then after I import it into the abacus, then the property of this is like elastic constant. Of the inclusion is elastic constant, but for the matrix it's the isotropic material. You just get density and the modulus, but for the inclusion plates it has it has 3 dimensions, the modulus in 3 dimensions, and several other things with the elastic constant I need to input. The model, I think the model means elastic constant. I think it's that elastic constant. Because I forgot a lot, because I haven't done this for a long time. I think it should be elastic constant.
Okay, thank you, Ming. And there's another question from Arnaud. I'm not sure if that has been answered already. I mean, wouldn't the negative Poisson ratio be improved with a...
No, sorry, I would like to ask something else, sorry.
Okay, please go ahead, Arnaud.
Sure. Ming, could you please share your presentation again and look at the 2-dimensional model at the beginning, if you don't mind, because I'm a bit confused. Where does the effect come from? Does the effect come from the fact that there is a gap, which has a funny shape?
So which side you want to go?
I would like to see some of the figures from your speak at the beginning. Yeah, from. Yeah, that is good. Yeah, that one is good. Yeah.
Yeah.
So the inclusion is just a gap. What is the inclusion here? Is it just a void, or is there something else?
It's something from this figure. This is our previous simulation work. This is just a gap inside the.
Okay, so you've got 2 materials here. You've got a matrix and air.
This is previous work. So this is just get some gaps inside these 2D planes to get this, trying to verify this structure working or not. But
cool. Yeah, no, sorry, no. Can you go back to a 2-dimensional model here? That one, yeah, that is very good. Okay, no, the green one, yes. So there is no carbon fiber shape here, right?
Well, for this one, it's just pure gap. But for this one, it's not. This one they get some materials inside here.
So what is the green material?
Green material.
Yes.
I'm sorry, I don't know this because this is not my.
No, but it's a matrix. What I'm trying to ask you is.
Literature.
What I'm trying to understand, because I think there's a confusion here.
They mention what this material is, but they just study the difference.
No, but is there something? Is there a material between the green and the white?
Yes, they just put the white with different or the white and the green with different modulus to test what kind of modulus gap is useful, because the gap between the inclusion and the matrix is from other literatures.
Okay. I think there is something quite confusing here in the fact that the effect is a geometric effect and comes from the fact that the white material is be it void or whatever, is a lot more compliant, and therefore it squeezes in a funny shape. I think the experiment you have made is, in order to get these gaps, you have to enclose them first, obviously. So you have to create these shapes, and that's why you put your... But the carbon fiber is very, very stiff, and the carbon fiber is kind of preventing the closing of these of the geometry. So that's why you've got 2 competing effects here. I'm not sure, but it's something is a bit weird in the way you are pushing it, I think.
But for my work, we are not doing but my work is not doing this. My simulation is this.
Yes, but the problem is that you have got too much. Okay, you have got three materials in your simulations. You have got your matrix.
Yeah,
you have got the void, which is air.
Solutions.
You have got air, and you have got carbon fiber to enclose the air. That's correct?
Yeah.
Right. So what is the real function of the carbon fiber? What I was trying to ask is, wouldn't your geometry work better if you had no carbon fiber at all? If you are able to have just air?
You just have air. If you only,
Yes.
you're trying to say, like, if you only put air inside you just create some like void space inside the
Correct.
matrix, then just you don't have any inclusions. They still have this function or not, right?
Yes.
No.
Well, how come that you have it? You just told me in the previous slide.
Yeah.
Here that it was just air and the matrix. That.
No.
Or even in the first one. No.
You get they get some kind. They get material here. It's not just air, and it's just like the material. It hides some void space inside the material.
Okay.
So
okay, that's good. Okay, fine. I believe you. That's great. I will look at these references. What is that? Who and?
Yeah. Okay. Thank you, guys. I mean, I think we probably have to. Yeah. I mean, we can probably take this conversation.
Yeah. Of course. Sorry.
Outside. Ming. You can share your email address with Arnold so that you guys can probably have a bit. I mean, spend more time on this, like having a chat about it. Thank you so much, Ming. Thanks for your presentation. So I will hand back to Frank.
Oh, excellent. Well, thank you very much, everyone, for participating. Thank you, Ming, for withstanding the questioning as well. Well done. Thank you, Dr. Nazmul Karim and Dr. Shaila for the question and answers. Well, the questions certainly, and some of the answers as well. Well done again. All the best to Ming on his journey back to Hong Kong next week. We'll miss you. I just want to invite you to not leave straight away. I'm going to switch your presentation off in a moment, but you're welcome to sit around the tables or virtual tables on the floor in a moment. But just want to say thank you again, and to also advise you that on the 4th of August, we will have another presentation from a printmaking collective. And oops, sorry, my camera has gone off. A presentation now on the 4th of August, the same place, same time. We'll meet here again at 12:30, and presentation will be at 12:45, and it's all about the diet of printmaking and photography. So thank you again. I shall turn off the recording. It will be available in full on the CFPR website sometime this afternoon. Thank you for coming. Thank you for attending. Thank you, Ming, for the presentation. And please feel free to stop by and say hello, and even continue this conversation via email or on the table. Thank you all. Bye.